Our next presenter is Dr. Rupik Biswas. Rupik is the chief of NASA's Advanced Supercomputing Division. He has a PhD in computer science from Rensselaer Tech. His talk today will discuss the scientific and engineering advanced computer environment at NASA Ames. Welcome to our conference, Rupik, and I think you're all set.
I'm all set. Yeah, thanks again. Well, thanks, Steve. Thanks again for inviting me here. I don't come here every year, but I like being here, especially during those times when the weather is good, like this time, even though it might be windy and chilly out there, but at least it looks nice outside your hotel room. So, again, I'm Rupik Biswas. I'm the division chief of the NASA Advanced Supercomputing Division. My talk today is slightly different from what I usually present, because what I'm trying to talk about here today is that, at least from a NASA perspective, it's a little bit more broader than just doing supercomputing in the traditional sense. So obviously, supercomputing is still the big 900-pound gorilla on the block, but it is more than just what we call traditional supercomputing in terms of, exascale and all that, because, DOE and Thomas Sterling and other people have all this under control, so I'm not going to worry about it. Let me just worry about things that NASA is interested in right away. And NASA, even though it's a fairly large agency, does not have the same amount of investments in high-end computing like DOE and other parts of the federal government. So let me just quickly set the stage, just in case you don't know this. Many of you probably already do, but you may have a very narrow view or a subset of the view of what NASA is all about. NASA has all these high-flying visions and missions that, after all, it's a government agency, so you have to have these kinds of things. But NASA is also, in some sense, a discretionary department or an agency. So in some sense, a lot of our success and funding and where we go depends on PR. It's whether the American public actually wants us to do the kinds of things that we do, rather than something that has to be done in some sense. But leaving aside the vision and the mission statements, if you look at how NASA is organized, NASA basically has 3 mission directorates. We used to have a 4th, but now that the shuttle is retired, that part of the agency has disappeared. And so basically, there are 3 main technical functions of the agency. One is aeronautics. That's the first day in NASA. Basically, the goal is to look at new flight technologies, environmentally responsible aviation, more secure and efficient aircraft, airspace management, all of that from gate to gate. All of that is part of the Aeronautics Research Mission Directorate. Is by far the smallest of the 3 mission directorates. It's only about $700 million annual budget out of an agency budget of $17 billion. So it's a really, really small part of the agency. And then the Human Exploration and Operations Mission Directorate, that's the new mission directorate that came into place after the shuttle was retired. And the main goal is, at this time, to support the International Space Station, which we have committed to do at least until 2020. But then also to develop new spacecraft, new rockets to get to Moon, Mars, asteroids, other places, both human and robotic exploration. So all that is part of the Human Exploration and Human Exploration and Operations Mission Directorate. And finally, science. Everything else that is left is in the Science Mission Directorate. It's basically broken up into 4 divisions. Earth Sciences, obviously. NASA, being a space agency, has a better perspective on Earth than anyone else. Any of the other agencies that are ground-based or maybe only go up to maybe 10 miles or 20 miles. Then we have planetary science, and then heliophysics, which is focused on the solar system, and then astrophysics, which is more like deep space. So when we are talking about advanced computing, you have to be able to support all of these things, and NASA is a mission-oriented agency, so you have to be able to do these things right away. The need for advanced computing, I don't want to spend too much time on this slide. I think everyone here is somewhat convinced that advanced computing is needed, whether it be data-intensive computing, whether it's supercomputing, whether it's cloud computing, all of that. I'm not going to dwell on this, except that from a NASA perspective, aeronautics, earth and space sciences, space exploration, all of these require orders of magnitude. If you ask the domain experts or you ask the technical staff, they'll always come up with requirements that require exaflops and exabytes of data tomorrow. Obviously, there's no funding that matches those things, and I think the scientists and engineers can always come up with problems that need to be solved that are significantly more resource requirements than you can possibly provide. So So from a NASA perspective, modeling, simulation, analysis is absolutely essential to rapidly and cost-effectively advance NASA goals. So that, I think everyone kind of agrees. It's good for, national pride and all of that. So, but then there is some realities. And so this is the driving forces. If you look at from a NASA perspective, I think people talked about this. There's budget crunches, and, at least in the federal government, you have to do more science with the same budget. Flat is the new high, low is the new flat. So all of this is reality. So the bottom line is you have to just make do with less resources. And then you have a bunch of other requirements. For example, as we see from all the various presentations, supercomputing capacity and capability needs to be grown to meet more requirements, exponentially increasing requirements. There is obviously high-end computing is a very niche player in IT, so you need to integrate new architectures and environments that better match NASA's requirements. You have to be able to leverage what's coming down from the semiconductor industry and other places. You have to assist a diverse science and engineering community to efficiently adopt and leverage this new hardware and software, because ultimately, peak numbers are one, and then actually getting value out of stuff that you have is a different story. NASA has a lot of data-intensive stuff, so improving data access bandwidth and latency to feed models and analysis is important as well. And then you have to do something with the data. NASA spends a lot of money putting satellites into space, and then it's not clear what we do with the data when we get that. So unless you're actually doing something with the data, you're just generating more data, and then the knowledge that comes with exploring that data. So all of that has to be done. So from a NASA perspective, if you look at what we mean by advanced computing, I would say that these are the 6 areas that we are currently looking at. All of these are not necessarily in the same level of maturation, and obviously in the center is the big supercomputing capability that we provide, and it's not just supercomputing, but it's production supercomputing. But we are also looking at a bunch of other technologies that could be valuable to NASA needs, and then we have to somehow evaluate them, benchmark them, look at them, and then mature them into the production environment. So that's the important thing. And I'll try to talk about all of these things today, given the time that I have. But let's start with supercomputing first then. Like I said, if you look at the NASA mission directorates, NASA has a very diverse set of requirements. On one hand, you have engineering requirements coming from exploration and station and all that, where engineers are running simulations. They don't care about 100,000 or 1 million cores. They just need to do a decision. As many of you saw this morning, ultimately it's a go, no-go decision. So they need to run a wide variety of parameter study cases when you're running the same code over and over again, maybe on 2,000 or 4,000 cores, but you need to run thousands of them in order to come to a decision. And traditionally, you could call them capacity. I would rather call them high throughput. And it's, even though that each of these jobs might be embarrassingly parallel and independent of one another, you cannot come to a decision until all of the jobs have actually completed. So it's a little bit different than a true capacity computing problem. And here's an example on the top right, where you're looking at aerodynamic database generation. So you're trying to generate a database at all possible flight conditions, and you're going to make some decision on the fly by going through that database. On the other hand, you have aeronautics and science mission directorates. They're research. They want to get the highest fidelity possible. You want to put 20 grid points in a core, in a vortex core of a helicopter. You want to model every tree on the Earth, which is apparently 3 trillion. So there you're talking about really, leadership class capability computing. We are trying to model as much possible with everything that's in there. And so you're now talking about exascale or large scale computing. And here's an example from, I would say, unsteady rotary wing calculation, where you're trying to capture, the highest fidelity and reality as much as possible. So that's another extreme. And then finally, you must maintain readiness. So for NASA, especially during the shuttle and even now, there are actual real circumstances where you must have things ready. You cannot wait for it. You have to have an answer within 15 hours or 20 hours or something like that. So if you look at it from a NASA perspective and you're looking at supercomputing, you must be able to combine, to satisfy or support all of these projects. If you look at Again, this is a very complex chart, but some of you may have already seen this, but this gives you notionally what we're talking about here. It's not just the computing, but the services that go with the computing. If you look, if you just follow that circle around and start from the top, for instance, you have these various NASA mission challenges. The supercomputing project per se is not supporting or funding any of those things. Those are being determined by the various divisions or mission directorates within NASA. But once those decisions have been made or the priorities have been established, we then come in and work with the domain experts to provide the performance optimization, the mapping of the codes to the architecture, helping get the best results out of what we have. It's all the support structure that goes with it, the storage, the networking, and all of that. And then finally, data analysis and visualization, as was very clear from Steve's presentation before me. Traditionally, supercomputing is all about computing, storage, and networking. That's, in fact, how supercomputing conference was started. That's what you did in supercomputing. You calculated stuff, you stored them, and you moved it around. That's all computing was. But when you have petaflops and exaflops scale computing, there's so much data is getting generated that visualization is now a key component of your overall ecosystem in some sense, and it has to be tightly integrated into the whole thing. Otherwise, and fortunately, unfortunately, traditionally supercomputers or processors and nodes are not graphics processors, so you don't really get computing out of your traditional computing hardware. So you have to have some other way of doing that. And then you feed all that back, so with the visualization, the data analysis, you're able to get a better insight of what you're trying to do, so you can actually decide what your next step should be. Again, a fairly busy chart, but I'm not going to go over this whole thing, but many of you already know this. You can look up what Pleiades is, but just the important thing here is that Pleiades, even though is a Xeon-based machine, it is a heterogeneous system in the sense that it has different versions of Xeon processors from Harper Towns all the way to Westmere's. I think it's about 1.3 or 1.4 petaflops at this time, and then it also has some accelerator cards in there. Just to see whether we can do some of that stuff, and then we are also adding Sandy Bridges that are supposed to be delivered later this week. And then it's all the balanced environment, everything that goes with it, and the facilities and all of that. So it's obviously a big operation, and this by far is the biggest activity that we're doing. Visualization, just one quick thing. For those of you who have visited the NAS division at Ames Research Center, you've probably seen the Hyperwall. This is the largest, highest resolution display that was ever built. At one point, this was the largest one in the world. In terms of resolution, it's at 250 million pixels. Obviously, it's very easy to beat this. Once you have resources, you can always add a row and a column, and then you can get a larger display. So that's not that hard to do per se. It's used in two different modes. You can look at single large images, which we do when we have governors and secretaries come in. But more interestingly, you use it as the parameter study case at the lower bottom, where you're looking at sets of related images. So the hyperwall, in some sense, is a cutting plane through a hyperdimensional space. And so as you move this plane, you can get different images, and all 128 images actually are in sync, so you can actually explore them. And if you have an expert in the room, you can look at relationships among the images to get greater information. Obviously, if you are there in person, it's easier to use the hyperwall, but we can also stream these as MPEG movies anywhere to your desktops. And smaller versions of the Hyperwall have been built. Everything is open source. You can do all of this yourself. Hardware is cheap. The software is free, so you can actually put it together. But what is more interesting is that we have developed this thing called concurrent visualization. So the Hyperwall is actually connected to Pleiades through the InfiniBand fabric. So in a sense that you can almost do real-time data analysis and visualization. So most of the time what happens is that you compute something, you store it, which is a bad thing because you're going to throttle your processor. You need lots of data storage to actually keep all the data. Then at some point, you're going to read everything in, and then you're going to look at it. And then like most of us, we're just doing research, so we have no idea what the hell we're doing. So everything is wrong, so you have to redo everything. And so what you're trying to do here is if you have concurrent visualization, you can actually look at your results while they're going maybe a time step or two behind. It gives you a lot of temporal accuracy, and you can change the numerical and the physical parameters as you go along. So again, That gives you a sense of what visualization is. Just to give a sense, the machine is extremely busy. The black line is 75% of peak. It's like a freeway. You shouldn't have more than that many cars on the road, but you can put as many cars on the road as you want, except that it all turns into a parking lot, but there's really no limit in terms of how many cars you can put on the freeways. But this shows, again, that it's a combination of these capacity and capability applications that keeps the machine extremely busy. But again, if you're interested, we can talk more about this. Just an eye candy chart of all the various things that are being supported by supercomputing. You have the shuttle at one point. We have the SLS. This is the new rocket, somewhat like the Saturn V, which is supposed to take us to Mars. This is the Space Launch System. Then, obviously, we have helicopter stuff that Steve just showed, looking at sonic boom optimization, looking at hurricane prediction, solving the Einstein's equations for merging black holes, looking at re-entry systems, looking at thermal protection systems for MPCV, which is the multi-purpose crew vehicle to bring the crew back. And then there are also things that happen on the launch pad itself. How are you going to modify the launch pad from a shuttle configuration to an SLS Saturn V configuration? And at the very bottom corner, right, you have when you have multiple SRBs, the solid rocket boosters inside the vehicle assembly building at Kennedy. What if one of them accidentally caught fire? You can probably take out all of Orlando or something, but what are those disaster scenarios? So again, this is kind of a quick summary of all the things that are going on in terms of supercomputing. But now, let's talk about these other things. And all of these things, like I said, are not at the same level of maturity, but we believe that all of these things need to be looked at carefully in order to understand that we are meeting NASA's requirements, which are very diverse. So accelerator technology, that's an obvious thing that comes up right away. There's always the need for accelerator technologies. There is this potential that you can execute many threads simultaneously at relatively low power. And in a sense, there are actually two options at this time. Either you can go with the NVIDIA GPUs, or you can go with the Intel Knights. But there are several concerns. First of all is, to what extent can science and engineering applications exploit these technologies? Obviously, both of these have pros and cons, and some have been around longer than others. But that's an important thing that you have to check, whether you can actually exploit these things, because there's always the peak numbers and then what you can get out of this. Programmability. Can you actually program your hundreds of thousands of lines of code to express the parallelism that is needed to exploit these technologies? Thomas Sterling talked yesterday about zillions or billions of concurrent threads, but can you actually leverage that? And then there is parts of that is the initial porting. You have a code, you have to actually port it over, and there is an optimization effort. We know that mics are probably easier to get running, but then you still have to optimize it, like Inglem was saying this morning, that in order to get the best out of that. And then there's also the learning time. There's a learning curve. It's not going to just happen overnight. And then the portability. Not only the portability of the code to future generations of the same architecture, so NVIDIA comes out with Teslas or Fermis and all that, and well, is it going to run forever, or am I going to be stuck on some day when I have to move it to some other place? Or if another architecture was more promising, can I move it to another architecture? It's not clear how much effort that is. And then from a NASA perspective, I think the first two can be done. If you threw money at it, sure, we can do it. It's not a big deal. Just hire a whole bunch of graduate students or programmers or whatever, throw money at it, and you can solve the first two problems. But the third problem is a bigger problem. How do I know that the results that are coming out of these things are actually the same results? I have no idea. I'm not going to send a Kepler mission off to find other planets based on some code that ran 1,000 times faster, but I have no idea if these are exactly the same results that you've gotten. And there is no way for me to verify or validate that, unless I try this for many, many years, which I've been doing all these last several decades. So that's the biggest problem. There are certain projects that are currently going on. For example, NVIDIA GPUs have talked about things, and there are many, many papers about how things have been sped up hundreds of thousands of times. But again, many of those things are looking at kernels. What we have been able to do is look at certain codes, and these are full production codes that are actually running well on GPUs. People have taken the effort to move them over, and these are applications that are running well. We have about 200 of these NVIDIA GPUs. 136 of them are actually in the Hyperwall. The Hyperwall being a 128 screen system has 128 GPUs, and there are 8 more in there. So they are connected. They're part of the Hyperwall of the rendering system, but they're connected to Pleiades through InfiniBand. And then there are 64 of these Tesla M2090s that are actually integrated directly into the Pleiades system. So So you can use these, and these are 4 cores that are really running on it. One is the GEOS code. This is from Goddard, looking at atmospheric assimilation, looking at heliophysics. The next code, this is with Lockheed Martin's Solar Lab. The third thing is with Langley. This is looking at landing gear noise. This is something that we probably don't care about too much, but landing gear generates a lot of noise, and the problem is that the landing gear noise is actually over densely populated areas, because you are actually deploying the landing gear when you're about to land. So that's an important social problem in some sense. And then with UC Santa Cruz, we are looking at high-resolution cosmological simulations. And then on the other side, we have the Intel mics, which we are evaluating at this time. We have several of the Knights Ferries in-house. We're looking at, again, I don't want to dwell too much on this, but there is the offload mode where you're running on both the, your Sandy Bridge or Ivy Bridge and your Knights Ferry, or you're just running in native mode. What happens? How do you actually do this? Do you have to write hybrid codes? Do you actually use all the mics with 50 cores or whatever you have in there, while your very expensive Sandy Bridge is sitting there idle, twiddling thumbs, not knowing what to do? Or should you actually write code that uses everything? Can you do MPI performance across nodes or within a node? All of that, I think, is going to be a part of this evaluation, and that's something that we're doing. The other, of course, is the next area is big data. Big data is apparently the theme of next year's conference here, and people have talked about it. I think Addison or someone mentioned that big data was not talked about yesterday, but I think too many people are talking about big data today, and maybe they're getting ready for next year's conference, I don't know. But the point is, from a NASA perspective, NASA has enormous collections of observational data. And simulation data, I think everyone has, but NASA has enormous amounts of this. And gaining knowledge or insights from this data involves a lot of analysis and analytics. And again, maybe everyone here in the room knows what analysis is and analytics is, but maybe I just have a couple of bullets on that. The analysis is a process of converting data into information. It's understood, it's easy in some sense, and you just have a lot of data, you just convert them to information. But analytics is a tool for discovering patterns in the data which may or may not exist, and then building predictive models. So you're going to say, oh, I saw that, and I see that's an alien life form somewhere. But that's something much harder. But for both of these, there are problems with the data movement and then searching this ontology to find out where we are. So one of the things that we have been doing recently is working with Cray very closely on the Eureka system, where we are looking at atmospheric data, series data that NASA has, converting them from HDF, hierarchical data format, to RDF triples, and then trying to see whether this is something that is useful as appliance. And I'm sure other vendors and other folks have similar things, but this is something that we are really interested in and trying to see if this is something that works. And again, one quick chart on Eureka. Again, if you have more questions about this, you should probably ask Larry or whoever the Cray people here are. In fact, this chart I've even put in the Cray logo down there, so whatever I say on this chart, I'm not responsible for this. But basically, it's a purpose-built hybrid system for interactive relationship analytics. So basically what you want to do is you want to do real-time data. You're looking at unstructured grids. So normally a MapReduce or a Hadoop cluster is not going to get you there because you are looking at unstructured data. You really don't know where the data, what the relationships out there are. So in terms of Eureka, and you can read more about this from the Cray websites if you want, but from a hardware feature perspective, what they've done is they've basically taken their multi-threaded architecture, their MTAs and all that, into this 4th generation thread storm. So you have multi-threading, so basically you have multiple threads, so if the data access stalls, you have these various threads you can do that, which is going to happen when you're chasing unstructured graph algorithms. So they have 128 threads. The C star actually can connect up to 8,000 of these processors together, so you can have 1 million threads going on simultaneously. They have a large shared memory. You can put in, I think, 64 gig per processor. So with 8,000 processors, you can put in, I think, 512 terabytes. And then they have a highly parallel I/O, which, according to their reports, move data at 350 terabytes an hour. So that's the hardware part, and basically the idea is that you are using multi-threading, large shared memory, and scalable I/O to solve this problem. And I'm sure SGI or IBM and other people have similar solutions. And then it's not just the hardware, it's the software as well. Everything is built out of open source. They're basically using the Apache Jena framework. the Java framework to do this, and then they have the Sparkle queries that sit on top of it. You can have various applications. You can have Linux applications. You have RDF. So RDF is this triple. So basically, all it has, unlike a relational database, RDF is just a triple. So it talks about the relationship and the two links at the two ends of that edge, basically. And then Eureka or Cray is going to develop vertical solutions later. It's all running with Apache Fusuki, which allows you to actually use RDFs and then do it over HTTP protocol. So that's what Eureka is. Cloud computing, that's another area. Cloud computing, there's a lot of buzz about it. There are people think this is a religious war between people who believe and do not believe in cloud, at least for HPC. They are being extensively used for commercial uses, but the question is that can you actually use it for HPC applications? NASA has first-hand experience with this. Many of you knew about or know about our Nebula project, which, by the way, has morphed into something else. And we had co-founded the whole OpenStack effort. And so the current focus is, can you actually use commercial cloud services for NASA science and engineering applications, and whether you can do something to actually improve the software or the software stacks that go along with those things. So basically, at this time, we have two objectives in this area. One is assess the feasibility of actually using commercial cloud services for NASA science and engineering tasks. So it's not just using it, whip out your credit card and get Amazon cycles, but this is the government. So you can't just whip out your credit card. It has to be the government's credit card. So how are you going to get the government's credit card? So there's all these policies, and how you're going to actually do this is a lot of work. It also has to make sure that we are not favoring one organization or one company over someone else. How can you make it easier for the user so that it's a web-based interface, so you're not actually putting all the effort or all the problems on the user's shoulders? What are the criteria that certain applications can actually run well on commercial clouds? And so that is one part of the effort. So actually see that whether you could use commercial clouds in some burst capability to actually support or augment needs that NASA has, while NASA gets its funds together or decisions to actually go and augment their supercomputing capabilities. The other aspect is, and this is something that we had done with the Global Grid Forum. Bill Feiereisen was the division chief. We were doing IPG. And I think in certain areas, NASA needs to decide that we can only contribute, but we cannot lead these things. And we have done those things, especially in Commercial Crew, for example. So we are not doing these things all in-house. We are giving it away to SpaceX or Virgin Galactic or someone else to build rockets for us. And so IT obviously is an even more easier decision to give it away to someone else. But the question is, can we work closely with them to improve the virtual environments or the software stacks that go on clouds, and maybe get rid of some of the performance issues or usability issues to make them more useful for HPC applications. So that's the second aspect of cloud assessment. One specific example of cloud computing is this collaborative environment. So that brings me to this third area, which is, if you look at NASA Earth Sciences, like I said, NASA gets a lot of data. There's a lot of data, but you need to get knowledge out of the data. So if you follow that kind of four-step process, NASA spends tons of money getting all these satellites out. We get a lot of data. Then you let us spend a lot of time processing the data, doing the synthesis, and then you get knowledge out of it, right? But the question is, it's a community effort. So unlike the other two areas, which are human exploration and aeronautics, Earth Sciences specifically is done by everyone. Someone could be sitting in North Dakota looking at NASA data and trying to predict what the weather is going to be in California. So you can do that, and that's how it's encouraged. But the problem is that there are hundreds of investigators who are spending a significant amount of time dealing with the data. And the dealing with the data could be ordering it, downloading it, pre-processing it, ensuring that the data is high quality, all of that. So you're spending a lot of time doing that. You're wasting storage because you have redundant storage saving all this data. And then you need to move increasingly larger and larger amounts of data to do this collaboration. So but the first three things, again, like I said, are bad, but they can be solved. If you threw money at it, you could solve it. Yeah. Who cares whether it's being wasted? Just buy more stuff. But the other problem is, which is the final problem, is that how do you capture the knowledge? What we get mostly out of these things is that you get a technical report. Okay, the technical report says something is happening. There's no workflow in there. There's no way to reproduce the results. There's no way to verify that these results are correct, and there is no way to further these results because you don't really know what someone else has done. So all these papers are getting generated without that information in there. So one of the things we have is this NASA Earth Exchange, which is a collaborative computing for global change. And so again, if you just focus on the stack, it's a software infrastructure. You have a support software that goes with it that looks at both the infrastructure software as well as domain software, and then there's a web portal. And then at the very top, you have the next science users who are approved users of NEX, who can go through the web portal or can go directly into the software to use the software to do, sharing the data, discuss, formulate new ideas, capture the workflow, capture the knowledge. Or you have the earth science community who are only allowed to go to the web portal, and so there's that black shaded bar, so they can't go into the actual software below it. And what this allows you to do is a combination of access to ready-to-use data. So all the data is already on NEX. You have all the models and analysis tools, and all the workflows are all there. So everything is in there. All you have to do is somehow decide how you're going to use all of this to generate the next level of data or the next level of knowledge. And that gets, again, added to this repository so that everyone can see what you've done. They can look at your workflows. They can look at what tools and what data you use, and then take it from there. And so this creates kind of unprecedented opportunities. Here's just two quick examples. One is the Landsat image at the top. So this is a 2005 Landsat mosaic. This is 9,000 tiles. This is 250 billion pixels. So that's 1,000 Hyperwall screens, by the way. And this is at a 30-meter resolution. So you are now looking at images that are half an acre. So you can actually, if you have a ranch somewhere, you have 2 pixels that are looking at it from Landsat. And now you can actually analyze and create quantitative information about these global landscape at your regional scale in 2 hours, for example. And you can look at deforestation, you can look at crop condition, you can look at water demand, all of that. Or at the lower end, you can look at 30 years of Landsat images and look at how things have changed over the years. So historical changes at continental scales or regional scales or whatever you want to do. So again, these are things that are being helped along by NEX. And then finally, probably the most controversial thing, and Thomas had a lot of good things to talk about this yesterday, and all the questions should be directed at him because he has spent 30 years doing this RSFQ thing. But again, this is something that we have recently gotten into. And by the way, that was going on while he was still at NASA, so we have a role in that. He can't claim all the credit. Here's a little rationale on the quantum computing stuff. Again, I don't want to get into this P versus NP and NP hard and NP complete. You can read it all up in Wikipedia. But the idea is that the core of many NASA tasks is actually optimization problems. So you're looking at search for planets, you're looking at remote sensing, precision landing, increased autonomy, all of these basically things that traditional computers have problems with. Image recognition. You don't know whether this is an apple or a grapefruit. Natural language processing. Machine learning. You're going to have these robotic missions that are going on to go out, and you have to make decisions on the fly right there. So technically speaking, at least the promise is, and maybe this is where cloud computing was or is, that quantum computing would solve such problems more accurately and more rapidly than may be possible. But here's a quick thing on, and again, I don't know how many of you are physics undergraduates or physics majors, but these are the little things that in quantum physics actually help you to do quantum computing. One is quantum superposition. That means you can have you can be in multiple states simultaneously that traditional computers do not allow you to do. Entanglement, that you could be in one space-time. This is all kind of magic in some sense. Quantum mechanics is. Wave interference, and then quantum annealing, which is similar to thermal annealing, that if you stayed at a state and you made minor small changes, you could stay in that state, and you want to get to this lowest energy thing. So again, since I'm running out of time, I just wanted to give you a quick tutorial on how you can program a quantum computer. This is one way of programming a quantum computer. Unlike a classical computer, you have input bits that come in, and then you have output bits. So these are ones and zeros, and you get ones and zeros out, right? But in a quantum computer, what you have are input qubits, which are, because of superposition, could be either in the spin up or the spin down place, which we in quantum computing are not zeros and ones, but are minus ones and plus ones. So there could be in plus ones or minus ones. So all these qubits are in that phase. And then you have this energy program rather than a math program or not a logic program, it's an energy program. And the energy program is basically going to convert all those qubits to a desired phase, which will be either spin up or spin down. So you're going to get -1s and +1s rather than being in some limbo. And so the energy program basically does is it's a control that drives all these qubits to be, that are originally in superposition, both in -1 and 1, to be slowly turned off, and then you're going to apply biases to the qubits, which in quantum computing are called the H vector. So you're going to apply H vectors to these qubits, and you're going to provide this matrix, which is J, to all the connectors. And then the process must be done slowly enough so that quantum tunneling can occur, but not slow enough that this will take for ages. And then the qubits will arrive at a configuration that is the lowest energy state. Another way of looking at it is that equations, for those of you who like equations, that's the Hamiltonian. And so the first sigma is is the adjacency matrix for all the spin ups and spin downs. The second one is all the energies of the qubits themselves. And then you have this annealing factor that you are going to slowly turn it off. And so you're going to get this Ising model. And so I have just one more slide. So we have been working very closely with D-Wave. By the way, before I show anything on this slide, if you go to the bottom lower right, it says D-Wave, the quantum computing company. And if you look at Cray, I think Cray says Cray, the supercomputer company. So something is wrong with the people in the Northwest, I think, part of the continental US, but they all have the same thing. But the D-Wave logo and the Cray logo are very similar. But again, a quick thing on D-Wave. We are working very closely with D-Wave. It's a quantum FPGA using the Ising model with superconducting flux qubits. So again, just quickly follow me on this. So that the very top left, what you have is the superconducting flux qubit. So it's made out of niobium, which is this niobium, which is different from silicon. So at supercomputing cool temperatures, it behaves. It shows quantum mechanical properties, so it can have superposition. So you have those, it has two very tiny magnetic fields, both up and down, so it could be in both states simultaneously. So once you have that one qubit, then you make several qubits. So that's the second image. So that's an image of 8 qubit loops. So now each of those loops, so that golden rectangle is that one loop, and then you connect that up through these coupling devices, which are the blues. And then you have a wafer you make, and so that's the Rainier processor that they have, which is 128 qubits and 352 of those couplers. Then you take that Rainier processor and you put it on the motherboard at the lower left, so that's how it looks there. And then you attach it to this refrigeration system at 20 millikelvins, which is actually commercially available right now. It's not that bad. And you can actually turn it off and off with a quick switch, and its maintenance is easy. And once you have that, you put it all in that black box, which is the D-Wave computer, which is 10 feet by 10 feet by 10 feet. So that's what we have, and I think I'm going to stop there. I'll be happy to take questions. Again, sorry for going a little bit over the time, but wanted to give you a quick overview of all the things that are going on. Thanks a lot.